All right, another machine learning relevant distribution for you. We've got the exponential distribution. So it's relatively squished up against 0 and then decreases exponentially toward higher values. So that might sound kind of like the log normal distribution that we just talked about, but the log normal distribution could take negative values and both increases and decreases before its peak. So it has an increase before its peak, before it starts decreasing, whereas the exponential distribution just starts at a really high value and starts moving away. So let's look at some examples of it. All right, so we'll use the NumPy random module exponential method to sample from an exponential distribution. And again, 10,000 data points. We're setting the scale parameter to 4. It defaults to 1. I just played around to get some nice looking distributions. I liked the look of this one. So you can see how all of the values are squished right up against 0, unlike the log normal distribution, which there's some squishing up against 0, but we also do have the peak slightly away from 0. So the exponential distribution, in contrast, starts at really high values right away. So the peak is right squished up against 0. And it wasn't the case in the log normal distribution that we did create, but log normal distributions could have negative values, whereas this distribution can't. So its logarithm also, another way of distinguishing it from the log normal distribution is that when we take the logarithm, again colored in brown, it still has some skew to it. It's not normally distributed, right? Whereas when we took the logarithm of the log normal distribution, it's perfectly normally distributed. So yeah, so related, but definitely not identical distributions. Some real-world examples of the exponential distribution include the time between requests to access Wikipedia pages, and this distribution is used frequently in deep learning. So deep learning models will often use an exponential distribution somewhere within them. Nice, and remember this guy from way back earlier in these live lessons, his name is Pierre-Simon Laplace. Well, we'll talk now about his Laplace distribution, which is closely related to the exponential distribution. Yeah, so the Laplace distribution is named after Pierre-Simon Laplace, whom we just saw the painting of. And so we mentioned him way earlier in these live lessons as a key figure in the development of Bayesian statistics. But I guess he was also important in discovering or describing this particular distribution. So we can, again, sample values from the Laplace distribution using a method in the NumPy random module. Again, we'll sample 10,000 values. And this distribution is alternatively referred to as the double exponential distribution. And you can see why, because it's an exponential distribution going both above and below 0. So whereas the original exponential distribution was just positive values only, the Laplace distribution, or the double exponential distribution, has that same shape on the positive values, but it also has the mirror image for negative values. So in addition to the scale parameter of the exponential function, this Laplace distribution has a location parameter that allows it to be centered on any value. So I oversimplified by saying it just occurs on 0 and is a mirror image over there, because we can change its mean and plot it anywhere, really. So, here it is again, but now centered at a value of 25. Okay, so some real-world examples of the Laplace distribution include extreme weather events. For example, the maximum rainfall in a day. And we see it in many machine learning applications. In fact, wherever we want an acute peak of probability in a distribution, you might go for a Laplace.